You might be interested in building a site for yourself and assume that you need to use a special tool to do that. But if you're a programmer, you can actually build your site yourself from scratch using any language you like. To do that, you might find it helpful to use the conceptual pattern at the foundation of the Web Origami project, which is something you can adopt whether or not you ever use any of that project's code. This video will explain the pattern in the context of building sites, but you can use the same pattern to create a wide variety of software artifacts. So to get started, here's a motivating computer science question. What's the data type of a website? If you had a project that built two sites and your code's main function held references to both of them, what's the data type of those references? I think having a good answer to that data type question enables you to entertain building a site yourself. So to make that case, I'm going to show the same simple blog built 6 different ways in 4 different languages. The reference blog is part of the Origami project. It's called Pond Life, which re-envisions Henry David Thoreau as a modern-day off-the-grid lifestyle influencer. So he's out there on Walden Pond, and he's writing these posts. He wants to have sort of the standard stuff you find in any blog. He's got next and previous links. He's got an index page with all of his posts in reverse chronological order. And then down at the bottom, his followers also can subscribe to feeds that he provides in different formats. So this is going to be our reference. We want to be able to build this particular blog in several different ways. So let's start by looking at the standard conventional answer to building a simple site like this, which would be a static site generator, or SSG. There are literally hundreds of SSGs. You can find them for any language, any stack. They all work pretty much the same. We'll just look at 2 of them here. The first is a very popular SSG called Astro. Like all SSGs, the way this works is that you're going to create your content, you're going to put it in a particular structure, and then you're going to run the SSG. It's a black box. You run it, it consumes that contents, and it outputs a folder with all the static files for your site. In this case, I've got the content available as markdown files here for each of the posts. And then I have a set of images for the project, and I want to turn these into the site. All SSGs have some degree of configuration, so you have to use a proprietary API to configure the SSG. And then to the extent that your creativity diverges from the sort of platonic ideal that the SSG envisions, you're going to need to describe how your site needs to be made. And you'll do that in code. You'll have templates. Typically, there are many different template languages. These will render objects like posts as text, like HTML. Astro happens to use a proprietary dialect of JSX for its templates, and then it also has blocks of code at the top of the templates. And those blocks of code actually add up. They're non-trivial because you need to describe in enough detail how your site works to Astro. In this particular blog, I wanted to have, it was important to me to be able to have the date of a post in the file name instead of as front matter metadata. And so to support that, that's not built into Astro. I need to do some work, write some code to parse the data out of the file name. So you end up writing a fair bit of code to get things to work the way you want. You're also subject to constraints. So in the case of Astro, I really wanted this images folder to be at the top level of the project, but Astro really wants it to be inside of a subfolder containing all the static assets, including style sheets, things like that. So even with all this code that you might be writing to use a static site generator, you're still going to be subject to their constraints. For comparison, we can look at a different static site generator. This is also very popular. It's called Eleventy. Eleventy does let me put the images at the top level of the folder. I'm going to sort of pay for that by writing some configuration code. Again, this code adds up, and again, it's using proprietary APIs. So here I'm going to use Eleventy's specific API to tell it where my images are. And I mentioned this point about proprietary APIs just to say that to the extent that you learn to use, these functions that are unique to Eleventy, they're not going to help you on the next project where you're building things a different way. That's just sort of the nature of projects like this. But it works, and many people are happy with these static site generators. I think that it's interesting to consider the value you get from a static site generator like Eleventy or like Astro. So if you're having to write a non-trivial amount of code, and you're having to learn a proprietary API, and even having done so, you're still subject to a significant number of constraints, then it's worth asking what value the static site generator is giving you and whether it's large enough to be worth all these costs. I think ultimately what a static site generator is giving you is a model, a way of thinking about how to represent your content and represent the site you're creating and represent how you're going to turn that content into the site. So you don't need to use a static site generator to get a model. You can bring your own model. So let's look at how we might do that. For a blog like this, it's helpful to recognize the fundamental tree nature, tree structure of a website, which is to say, if you took all the URLs in this site for every page, for every resource, and put those into some diagram, you might end up with a diagram that looks like this. This is a tree diagram. On the left, we've got the root of this site, and then we've got leaves like the About page and the feeds, and then sub areas, sub trees for the assets folder, the images folder, the posts, and so on. And this tree represents the complete site. If we had all of these files in this structure, then we would be done. So this represents the goal, the thing that we want to make. And we can also recognize that interestingly, that the source content can also be viewed as a tree. It's sitting on disk, and you've got an images folder with images in it and a markdown folder with markdown posts in it. So if both the source and the result of this process are trees, then your task of creating a site can reduce to one of transforming the source tree into the destination tree. So site creation and the creation of software artifacts in general can be modeled as tree transformation. To model a tree like this site tree, a very good, useful general representation of the tree, and this gets to the data representation question, is to think about each of the nodes in the tree as a map of keys to values. This is a fundamental data structure that shows up in many programming languages. Most modern programming languages have some way to do an arbitrary mapping of keys to values. Depending on the language you use, it might be called an associative array, a map, an ordered map, a dictionary. They're all basically the same idea. It turns out when you're creating software artifacts, the keys will generally be strings. The values will be text or bytes of a file. And then if you can also, if it's possible in the language to have a tree a map whose value can be another map, then you can compose these maps into a tree structure. So you can create a map-based tree. And that's going to be the fundamental data type that I want to talk about and show how you can do that in several different languages. We'll start with Python. In the case of Python, let's tackle a baby step. Let's say that we've got a small set of markdown files that say, hello Alice, hello Bob, and we want to turn this into HTML. Using this map-based tree pattern, we could say, okay, like instead of thinking about that as a folder of files on disk, let's think about that as a map of keys like alice.md to values like hello Alice. And our goal is to be able to create a corresponding tree of markdown where we have .html keys and HTML values. So to start, let's just say that we can represent this tree. We could use files, but let's use a dictionary in Python. This is the simplest way to represent a map of keys to values. This is a literal that you can have in your source code, and then you can iterate over the keys of the collection and then get each of the keys and values so we can, for example, dump this to the console. So if we run this, we see each of the keys and values. And this is a very common pattern in Python when working with dictionaries, is to do something with every key and value in a dictionary. We could, as I said, we could use the file system to read these files from disk, but to stay within this map pattern, let's actually represent the folder of files on disk as a map. So it turns out that Python has a very elegant collection of what they call abstract base classes. So that's a library, and it includes a class called mapping. Mapping is a definition of the shape of a dictionary, the set of things you need to implement for something to be treated as a dictionary. And it's pretty small. You need to define an iterator. This is going to produce the keys in your dictionary, and a method called getItem. Given a key, it should return the value for that key. And with those simple methods, we can create a map wrapper for a file system folder. So we can call our wrapper with a path to a local folder. It can return, we'll end up with a wrapper that has an iterator. This iterator will yield the set of file names for the files in that folder. And then when asked for the value that goes with a given key, that's just going to read the file from disk. And then it's worth observing that all this is lazy. So when we instantiate this map wrapper around the greetings folder, no substantive work is done. The work only really happens when we try and access the keys here by iterating, and then the values when we get the value for a given key. So that implementation is completely different. It produces the exact same results using the exact same code because this map is a dictionary. You can hand this map to any Python code that can accept a dictionary and it'll be fine with it. It doesn't need to know or care about the fact that that map is backed by the file system. And that turns out to be a very powerful abstraction. If we now want to take our map of Markdown and create a map of HTML, the simplest way to do that would be to do that eagerly with a Python dictionary comprehension. That would look like this. We get a reference to our map of Markdown, and then we use what's called a comprehension here. We're going to take each of the items in the Markdown map, and then we're going to change that. We're going to create a set of keys that end in .html instead of .md, and then we're going to change the Markdown into HTML using a Markdown processor. With that, we'll end up with a new dictionary that's got HTML in it, and we can iterate over that and display that just like we were before. Now the map is a map of HTML. This map the work here is being done eagerly. So when this code is encountered, it's going to read all the files from disk and turn them all into HTML. For a variety of reasons, particularly when serving a site and serving it locally or serving it live in production if you want to use a live server, it's helpful to have the definition of the resources in the site be lazier, to only do the work on demand. And to do that, we can create another kind of map that's backed by a source map. That is, we're going to use one map to create a live version that's a result. So we're going to do that by having a function. This function here is called transform. Given an input map of Markdown, this transform function is going to return a new map of HTML. It's going to do that lazily, and the way it does that is by creating a map that has the same mapping interface members. So it's going to return this right away, and that means that this call will do no substantive work. When this code is then asked for its keys, the iterator for our transformed map is going to get the original Markdown keys and turn them into .html keys on the fly. And when it's asked for a value like alice.html, it's going to get the corresponding source Markdown, alice.md, transform that to HTML on the fly, and return that. So this map is very lazy. It's only doing work on demand and doing as little as possible, but it has the same shape. So we can iterate over it using the same for loop, and we can retrieve a value using the same lookup. And with that, that produces the same result, but now it's being done in a lazy fashion. This is really all you need to be able to do. If you can if you can understand the code to write a wrapper around something like a file system folder as a map, and if you can write a function that will transform one map into another, either lazily or eagerly, then you have everything you need to be able to build a site yourself. You can compose these maps into trees and then use those to produce the files that you'll need to deploy for your static site. Let's look at that in Python. I'm not going to go through all the code, but the general idea is that we're going to have a file here that defines our site's tree of resources, and the core of it is a dictionary. This dictionary will define the root node, the root map of our site's tree of resources. And then it will define the values of those keys at the root. These are leaves like the about page or the feeds. And then here it's defining the subtrees, the folders for assets, the folders for images, and then folders for things like posts by transforming maps of Markdown into maps of posts. Now these calls, like this one to get a reference to the images folder, we can contrast that with the code that we had in our 11D configuration. So this is the corresponding code in 11D, but as I pointed out, this is a proprietary API. Like nothing else outside of an 11D project is going to use this API, whereas this code here to get references to the images folder as a Python dictionary, that is that the result of that is a stock Python object that you can use. You can use this project in this pattern in other projects. You could hand this Python dictionary to other Python code, and it would be able to work with it just fine. So this is much more native. This is doing things in a native Python way. To build this site's tree of resources, well, actually, first let's briefly just to show the laziness. We can serve this project locally, and so now we're seeing this is the live site that's being served out of the site's tree of resources. But for this particular talk, I just want to go through and focus on building. So we're going to build the tree of resources as static files. We're going to need a slightly more advanced folder map class. This is an expansion of the one that I just showed a minute ago. Instead of based on the mapping abstract base class, this is based on a related one called mutable mapping. And mutable mapping is the same as mapping. It just adds a few more members for things like clearing out a map, deleting items from the map, setting an item, so you can update a folder this way. And with that in hand, we can take our build process and think about it as a tree copy. We're going to take as input to our build our site's tree of resources as a map. We're going to get a reference to our local build folder. Again, this is going to be as a map, as a dictionary. And then we're going to call two standard methods defined by that mutable mapping interface. And these are available, this is standard Python. You can clear out the build folder to get it ready for a new set of files. And then we're going to call the update method on the folder. This again is a standard method. It will take each of the top level items out of the site and copy them into the build folder. So when we run our build, we get a build folder that has all of the HTML and feeds now realized as files on disk. And these can be deployed. You can deploy these to a static file server anywhere, and it'll be very cheap and fast. So this is the promise. This sort of delivers on the promise of a static site generator, but without needing to have recourse to an off-the-shelf tool. This code is essentially defining a bespoke static site generator for just your site. Okay, so that's Python. Let's take a look at a very different language. We'll look at a modern compiled language called Zig. Zig has strong typing and explicit memory allocation. It also has a much smaller standard library, so we need to do quite a bit more work in Zig, but just to talk a little bit about what that looks like. We can create an analog to Python's mapping interface. We can define a structure that's a little bit like the standard Zig hash map, only this one can be backed by anything. It defines at its core a key iterator and a get method that will, the get method will get the value for a given key. And once we have the idea of a map of keys to values in Zig, we can compose those maps into trees. And once we've got trees, we can specialize them. So we can create a tree of bytes backed by the file system. This takes, again, quite a bit more code because it's doing the memory management explicitly, but we have things like the ability to get a file from disk by name as implementing this get method, and then providing the set of file names that are in that map by reading the file names from disk. That can then be used to create the site's tree of resources. The Python version was pretty short. The Zig version is much longer. This is fairly sort of stock, boilerplate Zig code to get the, here, this is going to get a reference to our images folder. So this is much more verbose, but, it's also going to be faster. And there are, why build a site like this in Zig? Maybe you really love Zig, or maybe you're trying to incorporate this into a larger build process. So the build in Zig is going to look very similar to the build in Python. We get a reference to our site's tree of resources. we create a mutable file bytes tree that represents our build folder, and then we're going to clear it out and then copy our sites tree of resources into the build folder. And with that, we can build the same HTML and the same feeds, do all the same things that we did in Python, we can now do in Zig. We can do the same thing in almost any other language that you might come across these days. JavaScript, if we want to do it in JavaScript, that turns out to be only a little bit harder than Python, just because JavaScript's answer to the Python dictionary is a standard class called map. And the map class in JavaScript just isn't quite as elegant. It needs a little bit more reinforcement to be able to use it in the way that we want to be able to do it, but it's eminently doable. So here is the definition of the site's top level tree of resources. We're going to define a JavaScript object literal and then call a wrapper that's going to treat that as a map. We define the leaves, like the about page and the feeds here. And then here we get references to our local assets folder or images. And again, our build process is going to be one of copying the site tree into the build tree. So if we run that, we get our build folder. These builds are all very, very fast because there's very little code going on here. It's all code that we've written ourselves using this pattern. And then, this JavaScript code is actually a little more concise than the Python code, but we can get even more concise. So that leads to the fourth and last language that I want to talk about, which is the Origami language that's part of the Web Origami project. The goal of that language is to try and come up with a language that's as concise and expressive as possible for defining artifacts like sites, like these blogs. So the JavaScript code here that defines our sites tree of resources in Origami reduces to something that's much shorter. So this is the complete code for the top level of the site. The Origami language is a dialect of JavaScript expressions. Anything you can say in a JavaScript expression, you can say in an Origami expression. Origami adds some syntax that's useful for defining sites. The most prominent is that you can have file system paths and URLs directly as literals in your code. So you can refer to a file like about.md, or here we can get references to our assets and images folders just by referencing them as a path. If we step back, we can, if you remember in the Zig version, it took us 4 lines of code to get a references to the images. In the Python and JavaScript versions, it took us a line of code. And here in the Origami version, it's a single word. We also have reference to a number of built-in functions. The Origami runtime includes operations for working with trees, to paginate them, to map them, to flatten them, and to copy them. So there's a whole set of operations we've got, and that means that the build process for the Origami project likewise is extremely concise, so much so that it collapses down to a single expression. This is the build process. It's an expression that's going to copy the site tree of resources into the build folder. And that expression is short enough that we can hand that to the Origami CLI to evaluate it, and it creates our build folder. So we end up with the same site, but it's defined with a lot less code. To quantify what I mean by a lot less code, let's actually look at comparing these little projects. The purpose of having a reference blog is to be able to do apples to apples comparison, or as close as we can get to that. So let's look at the size of these projects. This is just counting bytes in the source code. So these are the 6 projects we've looked at. The 2 on the right, the static site generators. Keep in mind that this code is configuring a much, much larger static site generator. So in the case of Astro, this code is configuring something like 100 megabytes of node modules. The code on the left is creating a bespoke static site generator from scratch. And in fairness to those implementations, I think it's worth observing that a substantial portion of these projects are general purpose modules that could be reused on other projects of yours or shared with other people. These are very general operations, and so they can be shared. So I think it's worth thinking about that as something that could be factored out. And so if we look at just the code specific to this Pond Life reference blog only, we end up with this picture. And in this light, I think it's interesting that, for the Python and JavaScript implementations, they're actually quite competitive with the code required to configure the static site generators. So if we look at, say, Astro and JavaScript, for just this small delta, you're ending up with a much, much simpler world. You're working with standard language constructions, and you get to have complete creative freedom. There's no limit to what you can create that are imposed on you by the SSG because you're writing the SSG yourself. Another metric we can look at is we could measure something like build time. I do want to mention that all popular static site generators are extremely fast. So unless you have a truly massive project, build time should not be your primary concern. But we might as well measure it just to see what we get. Here, it's not too surprising that the Zig implementation ends up being the fastest. I was surprised that the JavaScript implementation here based on Node is very fast as well. V8, the engine inside of Node, is a very, very fast language engine. Okay, so I think this is a trivial blog. They all of the 6 approaches here build the blog in less than a second. A lot of this is startup costs. So if you were to have a blog with 1,000 pages on it, you would probably be looking at a build time for any of these that would be 3 to 5 seconds, something like that. Personally, I find that the clarity and the conciseness of the code is the most important thing when I'm looking at how I'm going to approach building an artifact like a blog, and the degree to which it's going to give me complete creative freedom. So I find that code like this or code for the Astro project, I find that to be both more verbose and sort of less expressive than defining something directly in origami. But there are all kinds of reasons that people pick different languages, and you should pick whatever language you're comfortable with. It's probably good enough to be able to build the site you're thinking of. I hope I've made a convincing case that you can build a site or something like this yourself from scratch using map-based trees in whatever language you like, and get better results that are as good as or better than using someone else's tool. If you're interested in learning more about this pattern or the Web Origami project, take a look at the project site at weborigami.org. If you have questions about applying these ideas, please let me know in the comments or get in touch via my profile page. Thank you.